All right, so for chapter 2.2, part 1, we're going to talk about density curves and normal distributions. Take a second to read pages 103 to 107. So what is a density curve? Why would we use a density curve? And what area is under a density curve? Also, how can you identify the mean and median of a density curve? So basically, a density curve is a smooth curve that describes the overall pattern of a distribution. Pretty much thinking like when I talked about throwing the blanket on a set of data to determine if it was like unimodal, bimodal, blah, blah, blah. Basically, the line that would follow, if you were to trace it almost, that sheet that you throw over the data. We want to avoid... the reason why we're using them is because we want to avoid estimating bar heights, counting lots of dots, etc. Basically, it allows us to look at our data and analyze it quicker. And lastly, the area under the curve and above any interval values on the horizontal axis is the proportion of all observations that fall in that interval. So basically, density curves have two requirements. One, they're always on or above the horizontal axis. And two, it has an area of exactly 1 underneath, or think like 100%. So in identifying the mean and the median, the mean is the balancing point, pretty much the spot where the curve would balance if it were solid. And then the median is the equal area point. It's essentially dividing the area under the curve in half. So let's look at a couple examples. These are 3 different density curves. So below we have our 3 different density curves, each with 3 points marked. At which of these points on each curve do the mean and the median fall? Take a second and see if you can figure it out, and then I'll give you the answers. So for A, the mean is at point C, and the median is at point B. For B, the mean and median are both at point A. The mean is at point A, and the median is at point B for graph C. Take a second and read about normal distributions on pages 108 through 109. What is a normal density curve, and how do you identify the mean and standard deviation? Basically, a normal distribution is described by a normal density curve. The mean is at the center, and the standard deviation of the distance from the center to the change of curvature points on either side. According to the CDC, the heights of 12-year-old males are approximately normally distributed with a mean of 149 centimeters and a standard deviation of 9 centimeters. Sketch this distribution, labeling the mean and the points 1, 2, and 3 standard deviations from the mean. Now you should remember doing something like this in Algebra 2. So it should be mildly familiar. So we're going to start with our 7 evenly spaced marks. Remember, the mu is considered our population mean, and the sigma is our standard deviation. So here we go. We're starting with our normal curve, where it has its 7 evenly spaced marks. Oh no, it's not showing up. All right, so we have our 149 being our mean. We have our standard deviation on either side. Notice how each is 1 standard deviation from the mean. The question marks up there are supposed to be the mean. It's just the mu sign. I don't know why it's not showing up. I'm sorry. All right. And so we know that each standard deviation counts as 7. So I'm going to put that on my graph as such. So 149 plus 7 and 149 minus 7 minus 7 minus 7. All right, and that represents the heights. Take a second to read pages 109 through 112 about the 68, 95, and 99.7 rule. What is this rule? When does it apply? And draw a sketch of it. So basically, this is the figure from your book, all right? Essentially, between the first and, for the first two standard deviations from the mean, that's 68% of our data. Between four standard deviations from the mean, that's 95% of our data. And six standard deviations from the mean, including both sides, is 99.7% of our data. This is also known as the empirical rule. So 68% of the observations fall within one standard deviation of the mean, 95%, 99.7%, you guys get it. And this is going to apply to all normal distributions. So using the earlier example, about what percentage of 12-year-old boys will be over 158 centimeters tall? So this is the chart from before, and we're looking at over 158 centimeters tall. All right, so that's 158 and on. So first we have to kind of get rid of what we know. So if we had 100% of our data, all right, and we subtract that middle part, all right, then we would know what that 158 to 176 and 140 to 122 would be. So that's why we divide it by 2, and therefore we get 16%. And then we're going to do the same thing. I'm sorry, I got cut off here. About what percentage of 12-year-old boys will be between 131 and 140 centimeters tall? All right, so note this is the distance between one standard deviation and 2. So we're going to take 95 minus 68, and we divide it by 2, and that gets us about 13.5%. Suppose that a distribution of test scores is approximately normal, and the middle 95% of scores are between 72 and 84. What are the mean and standard deviation of this distribution? So again, we're going to start with our normal distribution. All right, and we know that this portion in here is 95%. So that means on one end we're at 72, and the other we're at 84. And remember, these are all evenly distributed. So what we're going to do is we're going to take 72 and 84, subtract them, and divide by 2. This will get you your standard deviation. Once you have your standard deviation, you can figure out what your mean is. So my standard deviation ended up being 3, and my mean was 78. Can you calculate the percent of scores that are above 80? Not yet, but we will in the next section.